Our universe is a place of constant motion. From the smallest particles to the largest galaxies, everything is moving. Stars are born, live, and die in spectacular explosions. Planets orbit stars, their paths etched across the cosmos. Even galaxies themselves are engaged in a complex dance, drawn together by gravity's invisible hand. This cosmic ballet is a testament to the fundamental laws of physics that govern our universe. One of the most intriguing aspects of this motion is the rotation of planets and their orbits around stars. Why do planets spin? Why do they follow these elegant elliptical paths around their stellar hosts? The answers lie in the events that unfolded billions of years ago during the chaotic birth of our solar system. To understand these celestial motions, we must journey back to the earliest moments of our solar system's formation. This journey will take us deep into the heart of giant molecular clouds where stars and planets first take shape. We will explore the forces that sculpt these celestial objects, from the relentless pull of gravity to the conservation of angular momentum. Along the way, we will uncover the delicate balance that keeps planets in orbit and the intricate dance that governs our solar system. So, let us embark on this cosmic adventure, a quest to understand the fundamental forces that drive the motion of planets and shape the destiny of worlds. Our home, Earth, is a spinning sphere, twirling on its axis like a cosmic dancer. This rotation is responsible for the cycle of day and night, the rhythm that governs life on our planet. As Earth spins, the side facing the sun experiences daylight, while the opposite side is cloaked in darkness. This continuous rotation creates the 24-hour cycle that defines our days. But Earth's rotation is more than just a celestial timekeeper. It also plays a crucial role in shaping our planet's climate and weather patterns. The Coriolis effect, a consequence of Earth's rotation, influences the movement of air masses, creating prevailing winds and influencing the formation of hurricanes and cyclones. The speed of Earth's rotation is another fascinating aspect of this celestial dance. At the equator, Earth spins at a rate of roughly 1,000 miles per hour. This might seem incredibly fast, but because Earth is so large, we don't feel this motion directly. Instead, we experience the gentle transition from day to night, a testament to the smooth and consistent nature of Earth's rotation. Understanding Earth's rotation is not just an academic exercise, it is a reminder of our planet's dynamic nature, a celestial ballet that shapes our lives in countless ways. As we delve deeper into the cosmos, we will see that Earth's rotation is just one example of the intricate motions that govern our universe. To understand why planets rotate and orbit, we must journey back to the chaotic nurseries of stars' nebulae. These regions are the cradles of stellar and planetary birth, where the raw materials of the universe come together in a cosmic dance. These vast clouds of gas and dust are the birthplaces of stars and their planetary systems. Within these nebulae, the interplay of gravity and other forces sets the stage for the creation of entire solar systems. Within these nebulae, gravity acts as a cosmic sculptor, pulling together particles of matter and setting in motion the events that lead to the formation of planets. This gravitational pull is relentless, drawing in particles from vast distances. Imagine a swirling cloud of gas and dust, a chaotic mix of particles colliding and interacting under the influence of gravity. This turbulence is the birthplace of stars and planets, where chaos gradually gives way to order. As more and more matter clumps together, the gravitational pull of this growing protostellar cloud increases, drawing in even more material from its surroundings. This process is akin to a snowball effect, where the growing mass attracts more and more particles. This process of accretion, driven by gravity, is the engine of planet formation. Over time, these clumps of matter grow larger and more complex, eventually forming the building blocks of planets. As the protostellar cloud collapses, it begins to spin faster, much like a figure skater pulling their arms inward during a spin. This increase in rotational speed is a natural consequence of the conservation of angular momentum. This increase in rotation rate is a consequence of the conservation of angular momentum, a fundamental law of physics that we will explore in more detail later. This principle ensures that as the cloud contracts, its spin rate increases. This spinning disk of gas and dust, known as a protoplanetary disk, is where planets will eventually form. Within this disk, the seeds of future planets begin to take shape. Within the protoplanetary disk, dust grains collide and stick together, forming larger and larger clumps of matter. These collisions are the first steps in the long process of planet formation. These clumps, known as planetesimals, continue to grow through accretion, sweeping up more material from the surrounding disk. Over time, they become the building blocks of planets. Over millions of years, these planetesimals evolve into protoplanets, the precursors to full-fledged planets. This slow and steady process is driven by the relentless force of gravity. It is within this chaotic and dynamic environment that the seeds of planetary rotation and orbit are sown. The gravitational choreography of these early stages sets the stage for the formation of entire solar systems, each with its own unique dance of planets and stars. The spin within, angular momentum's influence. As the protoplanetary disk continues to spin, a fascinating phenomenon occurs. The particles within the disk, each with their own unique paths and velocities, start to interact in complex ways. The individual particles within the disk, each with their own momentum, contribute to the overall angular momentum of the system. This collective motion is what gives the disk its characteristic spin. Angular momentum is a measure of an object's tendency to rotate, and it depends on both the object's mass and its rotational speed. The more massive an object or the faster it spins, the greater its angular momentum. A key principle in physics is the law of conservation of angular momentum. This principle is fundamental in understanding the behavior of rotating systems. This law states that in a closed system like our protoplanetary disk, the total angular momentum remains constant. No matter how the particles within the disk move or interact, the overall angular momentum does not change. This means that as the protostellar cloud collapses and shrinks, its rotation rate must increase to conserve angular momentum. The cloud's spin becomes faster as it contracts, much like a figure skater pulling in their arms. This is akin to a figure skater spinning faster as they pull their arms inward, decreasing their moment of inertia and increasing their rotational speed. The same principle applies to celestial objects in space. This principle of conservation of angular momentum is crucial for understanding why planets rotate. It explains the rotational behavior of planets and other celestial bodies. As planetesimals accrete material from the protoplanetary disk, they also inherit the angular momentum of that material. This inherited momentum is what causes them to spin. This inherited angular momentum causes the planetesimals and eventually the planets they form to spin on their axes. The spin is a direct result of the material they gather from the disk. The direction of this spin is largely determined by the initial rotation of the protoplanetary disk. The original spin direction of the disk sets the stage for the rotational direction of the forming planets. In our solar system, most planets rotate in the same direction as the sun's rotation, suggesting a common origin, suggesting that they formed from a disk that was already spinning in that direction. This shared rotational direction is a clue to the history of our solar system's formation. This shared angular momentum is a testament to the interconnectedness of celestial objects and the fundamental laws that govern their motion. It highlights the intricate dance of forces that shape our universe. A delicate balance: gravity and orbital stability. While the conservation of angular momentum explains why planets rotate, it is the force of gravity that dictates their orbital paths around stars. This gravitational force is a fundamental interaction that pulls objects toward one another, and in the context of our solar system, it is the glue that holds everything together. Gravity acts as an invisible tether, holding planets in orbit and preventing them from flying off into the vastness of space. Without this force, planets would not follow the curved paths around their stars, but would instead move in straight lines, drifting endlessly through the cosmos. Imagine a planet orbiting a star. This orbit is not a simple path, but a complex dance influenced by multiple factors, including the mass of the star and the distance of the planet from it. The star's gravity constantly pulls on the planet, trying to draw it inward. This pull is stronger the closer the planet is to the star, creating a dynamic tension that shapes the planet's trajectory. However, the planet also has its own momentum, a remnant of its formation within the spinning protoplanetary disk. This momentum is a crucial factor in the planet's motion, as it propels the planet forward along its orbital path. This momentum propels the planet forward, tangential to its orbit. It is this forward motion that counteracts the inward pull of gravity, creating a stable, balanced orbit. The interplay between gravity and a planet's forward momentum creates a stable orbit. This balance is delicate and precise, ensuring that the planet neither crashes into the star, nor escapes into space. The planet's forward motion prevents it from falling directly into the star, while the star's gravity prevents the planet from escaping into space. This equilibrium is what allows planets to maintain their orbits over long periods. This delicate balance between gravity and inertia is what keeps planets in orbit around their stars for billions of years. Over such vast timescales, even small changes in this balance can have significant effects on the stability of the orbit. The shape of a planet's orbit is also determined by this interplay of forces. While some orbits are nearly circular, most are slightly elliptical, reflecting the variations in gravitational pull and momentum. Most planetary orbits are not perfectly circular but slightly elliptical. This ellipticity is a natural consequence of the gravitational interactions in the planet's own motion. This ellipticity arises from variations in the planet's speed as it orbits the star. As the planet moves closer to the star, it speeds up due to the stronger gravitational pull. When the planet is closer to the star, the gravitational pull is stronger, causing the planet to speed up. This increase in speed helps the planet to swing around the star and continue its orbit. As the planet moves farther away, the gravitational pull weakens, and the planet slows down. This deceleration allows the planet to reach the farthest point in its orbit before being pulled back toward the star. This continuous interplay between gravity and velocity results in the characteristic elliptical shape of planetary orbits. It is a testament to the intricate and finely tuned mechanics of our universe.